Okay, I've started the recording this time. So let's begin. Hope everybody can hear me. Let me know if you can't. Ask questions in the messages throughout the class. I really prefer some interaction. It's hard to speak to an audience I can't see. So just to recap briefly, last time, if you see the screen here, we went over in severe detail the 412 code, the 4-qubit code, to demonstrate how error detection works and why that specific code doesn't error correct. And then at the end, I made contact with several large and very useful classes of codes, one of which was the stabilizer codes. I showed for the few qubit example that the code words or the code basis states of the code form the joint +1 eigenvalue eigenspace of a set of operators called stabilizers. And these sets of operators are generated or can be expressed as products of powers of these three S1, S2, S3 stabilizer generators, namely ZZ acting on the first two qubits, ZZ on the last two, and X on all of them. All of these operators admit the code words as +1 eigenvalue eigenstates. And this stabilizer group, which is this set of all powers of products of these generators, these three generators, is an equivalent way to define this class of codes called the stabilizer codes. So a stabilizer, a group is defined to be as a set of, or a group of commuting operators that have such that the group doesn't contain minus identity. So each operator needs to have some +1 eigenvalues. Otherwise, there is no joint +1 eigenvalue eigenspace. So that's just a convention. But it's basically a set of commuting operators that admit a joint +1 eigenvalue eigenspace that forms a stabilizer code. And we're going to take this stabilizer code idea and run with it and port it over to the world of harmonic oscillators. Now, last time I mentioned stabilizers have a lot of advantage, namely these check operators, S1, S2, S3, are precisely the operators you would measure to extract syndrome information, namely to narrow down the error space that your noise has taken your code space into. So this stabilizer infrastructure automatically gives you a way to decode, or automatically gives you a way to characterize the different error spaces. And that same idea will carry through and be very useful in the bosonic picture. So today we're going to introduce bosonic codes or bosonic math involved in bosonic codes, and then we're going to talk about a subset of bosonic codes that you can collectively call bosonic stabilizer codes. In the next lecture on Thursday, we'll talk about bosonic Fock-state codes. Today, bosonic stabilizer codes is going to be three types, time permitting: analog, GKP, and GKP stabilizer. So let's begin with bosonic math. So what is a bosonic mode? Oh, and just before I forget, physical motivations for this will be made a little bit less obscure in the next lecture as well, but I'll mention them briefly today as well. So bosonic codes encode quantum information to the Hilbert space of one or more bosonic modes. A bosonic mode is also called a Q mode, or colloquially a harmonic oscillator. And these bosonic modes are ubiquitous in, at the very least, 4 different platforms in quantum science. And again, I'll go through this tomorrow a little bit more, but just to briefly name them: photonic, photonic degrees of freedom, translational or motional degrees of freedom of ions, microwave cavities, optical cavities, and that's, yeah, among others. And the point being is that all of these types of systems are modeled by continuous variable degrees of freedom, or CV, degrees of freedom. And these are different than what you would usually think of the qubit degrees of freedom as discrete. Here you're thinking of things that take on continuous values. Now, of course, all of these types of continuous real numbers that we'll be talking about today don't really exist in the real world because you can't write down a real number to infinite precision. So all of these in some sense are, models to something that in the real world is actually more coarse-grained, but it's very convenient to deal with these super precise real numbers, just like it's more convenient to deal with integrals than sums. So just to kind of segue gracefully into the bosonic world, I want to compare it to the qubit case. So in the qubit world, we had our states 0 and 1 for each physical qubit, and that was sort of our canonical, let's call it canonical or computational basis. And we associated each qubit with these two states, and you can equally describe them as being in one-to-one correspondence with the group Z2. Okay, the group of 1 and -1. Now, translating to the continuous variable setting, the quote-unquote basis that we're going to use for all of today, the only basis we're going to use for all of today, is an analogous continuous version of this Z2 basis, namely the basis that's labeled by points on the real number line. And we're going to basically use this basis to construct many of the codes that we discussed last time, thereby porting their error correcting capabilities into this bosonic world. So this is a basis for a single mode. And these states X are called position states. And I should use the word basis here in quotes for the following reasons, because while over here things were orthogonal and also normalized, this was the Kronecker delta function that was 1 if mu equaled nu, 0 otherwise. While here, and just a forewarning to the computer scientists, please don't be scared and run out screaming out of the room. I'm going to draw an infinity. This is called the Dirac delta function. It is not to be feared. Like this. It is not to be feared despite it being infinite when x equals y. 0 otherwise. Because as Dirac had suspected a long time ago, it really is a very nice analog of this other delta function, the Kronecker delta function. Now, having said that, we will have to take into account and pay the price for dealing with this infinity, but the price is not very steep. And the error correcting properties of these codes can be explained in a fairly slick way that isn't quite analogous to the qubit case. So that's why I have to use the word basis in quotes here. You can ask me what maybe more of the math stuff, what all this stuff means a little bit more technically, but we won't need that for this lecture. What we do want to, one more thing we do want to say is that this space that is spanned by this quote unquote basis is really just a space of functions that are physical, aka normalizable. So while the basis states are not, the position states are not normalizable, they do indeed form a complete set of states that you can use to expand any function. So I can take a function f of x and I can map it into a superposition of these basis states where the coefficient is just f of x. And I can map this function into a vector like this. And this is nothing but a tautological statement saying that I can write a vector in this space in terms of the basis of position states, because the position states resolve the identity. And the physical states, the real states that we're going to, eventually have to deal with in this bosonic Hilbert space are just functions that are normalizable. And by normalizable, I mean physical. They're basically the same thing in this context. But we want the norm of this vector so the norm in this vector in this vector space, if you think of it as just a normal vector space, winds up being just the true norm of the function, and we want this to be finite. So this is just nothing but the space of square integrable functions on the real line. And you can likewise think of this space over here as the space of square integrable functions on the group Z2. So in that analogy, let's jump now to using this basis to construct our favorite codes. Any questions up to now? Yeah. Yes, it's being recorded this time. Yeah. Yeah. The kind of person records their own stuff and then doesn't post it. So here we go. Here's some examples of codes. We're going to do today stabilizer codes, and we'll start with what's the simplest code that we went over last time? Anybody? Repetition code. So one example. The repetition code. And before, the repetition code consisted of encoding 1 qubit into 3, storing 1 logical qubit and 3 physical ones. And now this stores 1 mode, k equals 1 into n equals 3 modes. So we have a logical mode now. So the whole, our logical space is itself infinite dimensional. And we're encoding it into 3 similarly sized infinite dimensional physical spaces. And the encoding just takes the position state of our logical mode and redundantly copies it over 3 times. So k is just k is a discrete variable denoting the number of modes. So this thing is a basis for 1 mode. And n here is 3 modes. So this code is in one sense it's different because it's encoding an infinite dimensional amount of information. But in another sense, it's pretty much the same, because all we're doing is the encoding we're doing is very much the same. The degree of freedom that we're using to index the basis of our encoding is different. It's continuous now, it's infinite, non-compact, etc. But otherwise, this all looks pretty much the same. So you would expect, and this is true, that the error correcting properties of this code are also very similar. This code protects from errors that cause shifts in the position in any one of the physical modes. Remember, the other code protected bit flips, things that, exchange these. While here, this protects against shifts in, or position shifts, let's for short. On, in this case, a single mode. Right. And just like in the qubit case, there are unfortunately two types of noise here as well. So in the qubit case, remember, we were faced with not just bit flip noise, but also phase flips, which caused relative minus signs between the logical states. And here, the role of the bit flips is played by position shifts, while the role of phase flips is played by momentum shifts. And these, I'll define them later and describe why I call them momentum shifts, but in this, with respect to this position basis, momentum shifts cause phase errors or relative phases to change between these position states, just like phase flips caused relative phases to occur or change in the qubit case. And just like we saw last time, there is a dual phase flip repetition code. Here, there is a dual phase flip repetition code as well. And this one then protects against momentum shifts. And it uses these other states called momentum states, which I won't define a ket for them. I'll just write them as a superposition because we're not going to be using the momentum state basis, but I do want to just show you what it is. These are equal amplitude superpositions of position states. For now, the momentum, P being an R. And I want you to think of these as the oscillator or mode analog of the plus minus basis, which is an equal amplitude superposition of states in the qubit case. It's a dual Hadamard transform basis. In this case, it's not the Hadamard that does this transformation, it's nothing but the Fourier transform. And these momentum states can then be encoded in a repetition-like encoding, like the position states are here, to protect against the other set of errors, the momentum shifts. And so now we have our two ingredients and we can concatenate, just like we did last time when we expressed the 4-qubit code in a way that made it look like a concatenated code. So now we can concatenate. And we have our 4-mode analog of the 4-qubit code, the 412 code on the reals. And the code words here are again labeled by a real number. We're encoding one logical mode. We're concatenating, so we're taking a repetition code in the position basis. We're doing a logical Hadamard or Fourier transform. And then we're concatenating that once more as a phase flip repetition code, which obtains the 4-mode code. So this code, okay, recall the 4-qubit code detects any error on a single qubit. This code detects any single error on any mode. Now, So we've made some pretty good headway, but now let's go back and view and study this noise, these shifts a little bit more. Yep.
Hi. So my question is that
do you mind just texting the question?
Okay, sure.
And we'll get to it.
In the integration, you are y and b and not y and x.
Yes. Thanks. Yeah.
One question. So, unfortunately, I wasn't there last week, but we made it come up with this 412
Yeah, good. So the 412 code encodes one. This is NKD notation, where K is one logical mode into N equals 4 physical modes. It's a 4-mode code, right? 1, 2, 3, 4. And it detects any single mode errors, and the number of mode errors it detects plus 1 is called the distance. So its distance is 2.
And is it here that we can have any combination?
That, yeah, no, but of these NKD numbers?
Yeah.
No, there's definitely a lot of theorems and restrictions and bounds on these numbers, and that's a very well-studied thing, right?
And why is the team
I want to say it's just a convention, but I'm pretty sure I'm missing some deeper reason. This goes back to classical coding theory. I'll go with convention for now.
The question for phase wave repetition code, we have 0 going to plus 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 and 1 going to minus minus minus. What would it be for the continuous case?
In the continuous case, you would have let me do this in a different color because I'm not going to use momentum state basis. I'm only dealing with one basis the whole lecture. But since you asked, let's define this to be momentum basis, and the phase loop repetition code encodes a logical real valued degree of freedom into this momentum basis. Okay. So let's go back, and we've made a lot of headway now. We've basically caught up to almost the whole error correcting strategy, but let's go back and see what the structure is of our noise a little bit more. And the noise, the analog of the Pauli's that allowed us to make so much progress yesterday is the displacement operators. And these are precisely these shifts or displacements by some amount of the position or momentum degrees of freedom. So for a single mode, these act, I'm going to write them like this and explain them a little bit, but they act, I'll tell you how they act. They act on a position state like this by, these are position shifts. They shift the position state. And then the momentum shifts act as follows on the position state. They give you a phase that depends on the value of the position state. So this I want you to think of as an analog of sigma x. This I want you to think of as an analog of sigma z. So position shifts are not diagonal, are extremely off diagonal in the position basis, and they are very much diagonal, or momentum shifts are very much diagonal in the position basis. If you look at things in the dual momentum state picture, then position shifts are diagonal in the momentum state basis, and they're very much off diagonal. The momentum shifts are off diagonal in the momentum state basis. So the word shift here is used to basically denote off diagonality. And right now, the way I've written these, so these are position shifts. And these are momentum shifts or displacements. I've written these in terms of exponentials of these operators, p hat and x hat. And these are operators on this space. You can call them quadrature operators or just position momentum quadrature operators, satisfying the famous commutation relation. Xp minus px is I. And just like before, general errors can be expressed as powers of products or as as combinations of tensor products of displacements of shifts. So last time we looked at Pauli noise, so bit phase, and then we looked at superpositions of any of those three plus the identity. A similar picture holds here. If you can show you correct against a position shift, a momentum shift, a product of the two, then a general error you can correct or detect respectively by just expressing it as a superposition of these. And physical noise allows you to do this. Okay, so now we've introduced, so this concludes the sort of push of oscillator math. Now we go into more general class of codes that generalize the repetition code and the 4-mode code. Any questions now? We're good? Yeah.
Position shift, does that have to be an infinitesimal shift?
No, so in this case, any position shift will do as long as it's on a single mode. So for these types, so there's going to be lots of different, there's going to be two different versions of small here. Here, small or the correctable noise is noise that acts on a few modes only. In this case, in the 4-mode case, only one mode. But the magnitude of the shift on that mode can be arbitrarily large. Remember, any single mode error is detectable for this 4-mode code. Later on, we'll get to a class of codes that can actually detect and correct shifts acting on all the modes, as long as those shifts are sufficiently small. So you see there's a very big difference in the noise models here. Here, the noise is characterized by weight. Weight is the support or the number of modes a displacement or a shift acts on non-trivially. This weight 1 errors are detectable by the 4-mode code. But in a class of codes like the GKP codes, the notion of smallness of noise is the amplitude Q that the displacements have.
Are these codes practical because it seems like a small noise model is more likely than.
Correct. These codes are not practical, but they offer a nice gateway connection to the repetition codes, which we saw last time. And they offer, on the other side, a gateway into the more practical codes that we're about to see. So this non-practical class of codes is called analog stabilizer codes. And this is sort of the naive extension of the qubit stabilizer formalism to bosonic modes. For the 4-qubit code, or sorry, for the 4-mode, the 4-mode code can also be expressed as a stabilizer code with a stabilizer group. It consists of all powers of products of 3 generators. And these are displacements, so we have to take all the possible powers of displacements, which are all the real numbers. You can displace by any real amount, and it yields a different operator. And here, the three stabilizer generators are the following. This one's the difference of positions. So this I want you to think of as the analog of the XXII stabilizer generator for the 4-qubit code. This one you maybe guessed it is the analog of the IIXX. And the third one is the, sorry, CZII. This one will be the 4X's. Notice there's some more minus signs that come into play here to make everything commute. As soon as you get away from binary, you have to start worrying about minus signs. And these SIs, their joint +1 eigenvalue eigenspace is precisely the 4-mode code that we reviewed or introduced up here. So in that sense, this is a very close analog of the stabilizer codes. And error spaces now are labeled by these ABC elements of that correspond to the powers of the stabilizer generators for the stabilizer group. Notice that error spaces are labeled by a continuous number. So that sounds a bit problematic. But because of this, there is actually something that simplifies. This group, stabilizer group, is continuous. And if you remember something about Lie algebras and angular momentum, continuous groups, it often pays you to bring the stuff in the exponent downstairs and just look at that stuff. That is called the Lie algebra of a Lie group. And that's what is possible to do in this case using the nullifiers, which are the Lie algebra of the group, which in this case are just x1 minus x2, x3 minus x4, and the p's. Now, here's the equivalence that allows you to do this. Any state that's stabilized by a stabilizer generator, an exponential of one of these nullifiers, is automatically guaranteed to be, let's call these etas. So if a state is stabilized by eta exponentials of eta for all a, then that state is automatically annihilated by eta. If we can take any power of this non-compact displacement operator generated by eta, we can take any power a of it and still get a +1 for the code state, then we might as well just look at the generator of this thing in the Lie algebra sense and bring that downstairs, and you'll see that it just winds up annihilating the state, because otherwise we would not be able to get the left-hand side to work out for any value of a. For example, for the 4-mode code, if we look at the annihilator or the nullifier, the annihilator is another name for these x1 minus x2, we write out the state. Sorry, y dz. We write out the code word. Plug in the nullifier here, Well, x1 is a position label. x1 hat is a position label, and it acts on the first mode. So that'll just spit out y. The minus goes along for the ride. Yes. There's a request to do live transcription. What? Well, I mean, we're already halfway through the lecture. Maybe next time we can do the transcription. I'll have to play with that a little bit. So the minus is coming along for the ride, and x2 hat is acting on the second mode. Sorry, I didn't really define these operators as I'm using them now, but I hope it's natural, and please ask a question if it's not. x2 hat is a position label for the second mode, and so it just spits out, it's diagonal on the position basis, it just spits out the label of the second mode, and you get y minus y, which is otherwise known as 0. So that shows the right-hand side of this equivalence. So these nullifiers give you several advantages. First of all, measuring them is fairly physical process. It's called homodyne detection, and they allow you to diagnose the syndrome. So in this case, the syndrome is a continuous variable, and there are as many syndromes as there are nullifiers, and measuring the nullifiers gives you the syndrome. So instead of measuring, phases of a unitary operator like we had before with ZZII, XXXX, now we're measuring the in the position or the eigenstate basis of these nullifiers, which have real spectra. They're also Hermitian, they're self-adjoint, so you can use homodyne detection for them. And this, despite the previous comments about impracticality, this is something that's fairly ubiquitous in one approach to quantum computing called cluster state, bosonic cluster state, or continuous variable cluster state computing. They've made, so a cluster state is just a stabilizer, a particular type of stabilizer state, or analog stabilizer state that's annihilated by some nullifiers, and they've made these things on a bunch of different modes, multiple modes. I don't want to say how many because I forgot, but they have been able to stabilize these fairly entangled cluster states, analog stabilizer states, on very many photonic modes. You can go to the error correction zoo. There's an entry about that. I think cluster state or bosonic stabilizer codes, dig around in there and you'll find the references. Yeah.
What would be the qubit analog of the nullifier?
There isn't one, right? You can't, it's because of this that we have a nullifier. Before in the qubit case, we had only binary entries in our powers because we had Pauli matrices. And so there's no good notion of taking the logarithm and bringing stuff downstairs for the qubit case. It's only in this case that we get one. And just in case you were getting used to it, we're about to go away from the nullifiers again, because the displacement group is actually even richer than that, and it admits groups that are discrete and not continuous, which thereby does not allow you to use nullifiers, but nevertheless yields a different type of bosonic code. Yeah.
How do you physically generate continuous cluster space?
There's photonic schemes that do this. Beam splitters, phase shifters. I think that's so because the nullifiers are pretty simple for those states. Maybe even some you can do with Gaussian type processes. I'm sorry if I'm saying things that you're not familiar with, but the reason they're popular is because they can be constructed with fairly simple ingredients from photonics. I don't necessarily want to go into those ingredients here, though.
Can you go through the steps of getting the Y outside?
Yeah. So what we had here actually first was we commute x1 through the y, like this y, the one I'm doing, okay. we had that. And now that equals x1 can alternatively be thought of as x tensor identity tensor. Here, for the computer scientist, this will make you happy. And x2 can be thought of as identity tensor x tensor identity tensor identity. And then x hat is to go from here to here, I have to define this operator. Thank you for making me define it. I did not. This is literally the operator just assigns it just puts the label as a coefficient next to the state. And when you do that, you get y times identity, tensor identity, tensor identity, tensor identity. Right? And then the same thing, and then we're back to here. Okay. All right, so now we'll leave analog stabilizer codes and we'll move on to our second class, the GKP codes. So far, we've been dealing with bosonic codes that encoded a logical number of modes, k logical modes into n physical modes, namely an infinite dimensional logical space into some tensor product of infinite dimensional physical spaces. Now, we're going to show how a similar approach using stabilizer groups will allow you to cook up codes that admit a finite dimensional logical space, but that are themselves embedded into some amount of physical modes. And these codes are called the GKP codes, named after Gottesman, Kataev, and Preskill. And these codes protect not against arbitrarily large errors on a few modes, but against sufficiently small displacements that can act on as many as all of the modes. So I mentioned this switch in the noise model. This is where this is going to happen. So above we had a set of commuting shift operators that formed our stabilizer group. But it turns out that displacements can commute with each other, even for one mode. So before we had the 4-mode code, we needed 4 modes. But you can play this game even for 1. So recall, well, maybe not recall, maybe you're going to see this for the first time, but the commutation relation between 2 different displacements on a single mode is as follows. You take a position shift by Q1 and try to permute through a momentum shift by Q2. And what you get after you permute one through the other is the 2 permuted and a generalization of the minus sign that occurs in the Pauli matrices that now is a full-blown phase that's just related to the product of Q1 and Q2. I want you to think of this as the analog of the commutation relation between Pauli X and Z. But now, because we have these continuous degrees of freedom in Q1 and Q2, it is possible to fine-tune them to make sure that these commute. If we let Q1 equal Q2 be square root of 2 pi times some natural number n, then the phase reduces as e to the 2 pi n, otherwise known as 1, which means that if we plug that into here, these displacements by square root of 2 pi n actually commute with each other. And here is, I guess I would like to remind you that there will not be any nullifiers, because if we take everything downstairs, the commutation will no longer hold. X and P don't commute. And any scalar times X will not commute with any scalar times P. So this is not like the nullifier thing where the nullifiers themselves did commute with each other. Here, it's the exponentials at particular values that will commute. So we can define a stabilizer group now that we have a commuting set of displacements. And that is the stabilizer group of a particular GKP lattice. Sorry, getting ahead of myself. GKP code. It's generated by these two elements, namely, it's all the powers. Let's call this S1, this S2, and it's the set of all powers of products of these elements. And now the powers that we're allowed to take, such that these things still commute, are just integer powers of these displacements. Because if you don't do integers, then the commutation relation won't work anymore. This is yet another group. We have a different domain. Again, we had Z2 for qubits. We had R for the A's and B's for the analog stabilizer codes. And now we have Z integers for all the different powers that we put into our GKP stabilizer group. So this is a discrete group. It's a discrete infinite group, but nevertheless, it's discrete. So there's no nullifier analog. And just as before, these stabilizer group elements admit a joint +1 eigenvalue eigenspace, whose states are the logical, whose states are the logical code words of the GKP, of a GKP code. What do these states look like? Well, let's think about it. If these states are invariant under the stabilizers, they're stabilized at +1 eigenvalue eigenstates. And the stabilizers here are shifts by discrete multiples of square root of 2 pi n in both position and momentum. So let's look at our favorite position basis. We want a state that's constructed as a superposition of some position states, such that when you shift the positions all by some fixed multiple of something fixed, they go back upon themselves, because the state should be left invariant. Now, what, if you remember your solid state physics, what is a structure or a set of points such that when they're shifted by some particular constant is left invariant? A lattice, that's right. And GKP states are nothing but a lattice of position states. There's two of them. So there's basically two different, there's going to be a lot of lattices, unfortunately, but the spacing between the lattices here is the same. So this one is going to be all even multiples of square root of pi. And this one will be all odd multiples. So these states respectively consist of position states labeled by points on two alternating 1D lattices whose points are spaced apart by 2 square root of pi. I'm sorry, I made a mistake, not square root of pi, 2 square root of pi because of the 2. So we can start to draw that a bit. Here's our real number line. And I'll draw black and white balls on it. The black balls will form the lattice of the logical 0, position states. And the white balls will form the logical 1 position. Okay, just as a sanity check, let's see whether these words are indeed the +1 eigenstates of the stabilizers. Go back to the stabilizers. Here I've plugged in capital N equal to 2. So if we plug in capital N equal to 2, the stabilizers are 2 square root of pi. Shifts in position momentum. Now these are all position states, so they're automatically eigenstates of this operator, of the momentum shift operator, because it's diagonal on the x hat basis, or on the x basis. And their eigenvalue is all the same, because if you multiply 2 times square root of pi times x hat, which gets substituted with 2l square root of pi, you get 2 pi l. And e to the I 2 pi l is otherwise known as 1. So we're good here. For the momentum, for the position shift, now we have this lattice effect happening, that you have this 1D lattice and the states are shifted by 2 times square root of pi. Well, that's precisely just a linear shift on the balls. Like that, and because there's an infinite number of them, they're all left invariant. So this stabilizer is also checks out. Now, what does this code protect against? Well, we remember our intuition from the 4-qubit code. To protect against bit flips, we learned yesterday that the states participating in the logical 0 and logical 1 states need to be somehow far apart. They were far apart in the Hamming distance yesterday. Now they're far apart in the normal distance on the real number line. The black balls and the white balls are spaced far apart from each other. And any shift that does not map one into the other is detectable. Right? As long as, remember, what we learned, if there's anything we learned yesterday, is that what is a detectable error? Any error that takes you out of the code space. Well, the code space is just these cones of specific belonging to these 2 lattices. So anything that maps you out of those states is detectable. So a displacement so here I've highlighted the values of Q of the position shifts that are detectable. And if I highlight them all on this number line, I get a unit cell between square root of pi and pi, representing all the different values of position shifts on the single mode that are detectable. And this is just because the spacing between the 2 code words is 2 times square root of pi. Yes?
Does it make sense to somehow, because you said in the manual code,
Yes.
but is it somehow possible to do some
Yes, then you get what's called a Hilbert space of a linear rotor or particle in a ring. And then you get the rotor version of this GKP code. These states were not prepared for 20 years after they were created, theoretically. And then they were prepared in the last few years in 2 different platforms. It turned out that using certain quantum systems, it was easier to prepare the oscillator states versus the rotor states. The oscillator is a little bit more ubiquitous, but the mathematically and in terms of the protective properties of these codes, they're all the same, basically.
Sorry, one more. in the previous code, there was some continuous variable states.
Yes.
Whereas here is it true that here we have a qubit which is encoded in these
Yes. No, it's a qubit now. That's right. There's two differences between these and the analog stabilizers. One is the noise model. They protect against sufficiently small shifts of a single or more modes. And then here they're encoding a finite dimensional logical state space, a logical qubit, which is really what we need for a quantum computer.
Related question is, how does one encode Bosonic states themselves? But these are encoded.
Right. So these position states have different correspondences depending on which platform you look at. They can represent the position degree of freedom of a trapped ion. They can be related to how many photons are occupying a particular photonic cavity or microwave cavity that's been cooled down to the point where you can resolve the photons, and so you have to start worrying about counting them. And depending on these platforms, there's various different tools and techniques that are applicable and can be used to create these states. Sometimes the creation process is deterministic, and other times it's probabilistic. It's not always very easy to create exotic states in the lab, and different platforms are suited for different states. Yeah.
For changing our defining our length of state, why are we standing over all of these values that way?
Because otherwise we won't be invariant under this. You know, Hilbert's hotel will shift and we'll have one left over. We got to have them all turtles all the way down. Yes.
Why want to use variable?
What?
Why do we want to use variable?
Well, it turns out this code is actually quite powerful. It's encoding in an infinite space, but it's encoding only in a single mode space, an accountably infinite space. It's encoding a finite dimensional subspace. But it's protecting against a continuous stream of errors, a continuous set of errors. Q here, the yellow region is a continuous region. And this type of protection against a continuous set of errors, in these lectures, that's the first time we see this for a discrete, for a finite dimensional logical encoding. We didn't have this for qubits. So in some sense, there's a lot of information that can be gained by encoding and protecting this way. This is why we're studying it here. And this code is using the stabilizer framework. And so the stabilizer convention, I guess that's the easier answer. The stabilizer convention is such that there's some set of operators that are defined, and the code space is the +1 eigenspace of these operators. And remember, the stabilizer infrastructure gives us error syndromes that allow us to label error spaces. If I just gave you two states out of the blue without telling you anything about them, you wouldn't know what error syndromes to measure. You wouldn't know what circuit, how to do a round of error correction for them, much less decode. And the stabilizer formalism helps you do half of that. It helps you figure out what to measure. What are the syndromes? What are the operators you need to measure? The check operators. As far as decoding is concerned, it also helps you gain headway there, but it doesn't overcome the complexity of the decoding problem in general because of the exponential difficulty. In this case, it's a single mode. There is no exponential blowup. You just assume that the most likeliest error is the smallest shift, and then you just, if your shift is happen to be here, then you can correct back, and if it was large, sorry, you can detect it, and if it was larger, you could not. Let me cover a little bit more of the properties of these things. Yeah, go ahead.
Is an operation that takes you from 0 to 2 square root of 5, is that an
Yes, that's an error if you didn't know it happened. An operation that takes you from 0 to 2 square root of pi, because it took the white balls to the black balls and vice versa. Sorry. Oh, right. Took the white to the white. That specific operation is not an error. It's the operation that you get when you apply this stabilizer. Right? And a stabilizer leaves the state invariant.
And then can you resolve smaller errors in position by decreasing Q1 and changing Q2 the delta product?
Yes, yes, you can. Good question. You're thinking a few steps ahead. I've only covered position shifts so far, but might as well say that there's a dual way to write these codes that allows the same argument that I made here to be made against momentum shifts. So in one fell swoop, I can say that the region that I am outlining here in the yellow is the region of detectable position and momentum shifts. Sorry, what was the question again?
Can you detect smaller errors in position by decreasing Q1 and
Right.
increasing Q2?
And so now you can sort of think of this as a square if you do superimpose or sort of combine both segments. And this square can be deformed into a rectangle that allows more protection against one of the quadratures at the expense of lesser protection against the other. This should be thought of as the similar effect as what we saw yesterday with the quantum parity codes, where we had two variables M1 and M2, each of which corresponded to the concatenation of the bit and phase flip codes of the phase flip and bit flip repetition codes that we concatenated. And the higher M1 was, the more bit flips we could protect, and the higher M2, more phase flips. But if the total number of qubits, which is M1 times M2, is fixed, then the larger we can make M2 to protect against one type of noise, the smaller M1 has to be to protect against the other. The same type of trade-off is evident here, and this type of trade-off is pretty universal in quantum error correction. Yeah.
How do we define distance for this code?
Good. The notion of distance has to be different here because we're dealing with shifts that are detectable that if they're only sufficiently small. So let me go through the correctable shifts and then the distance is just the magnitude of the largest correctable shift in this case.
So this one again, this is
So displacements, just like the Pallies, the question was, does this protect against other things like squeezing or any other operator? Displacements, just like Pallies, allow you to express physical noises in terms of superpositions of products of Pallies and or products of displacements. So if for any physical noise operator, you can express it as an integral over different displacements with some coefficients. If the coefficients are concentrated around the small displacements, then that operator is more or less correctable. And if not, then you're out of luck. And so far, we've seen that a lot of physical noise, or the dominant sources of physical noise that we've seen in the lab, are indeed supported on few displacement operators, or the small displacement operators. And that allows you to at least infer the GKP codes should do pretty well. So squeezing you is a coherent error. It's not trace class, so you cannot, without something blowing up. But squeezing would probably not be a very good error for these codes, because if you think of an infinite lattice, squeezing is sort of like a shearing transformation on the phase space, on this position momentum space of the oscillator. And if you're very, very far from the origin, you're going to get taken away to a very different location. So squeezing, I guess, is actually one of those errors that is not very well protected. Rotations is another one that's easier. If you just rotate position into momentum, then as you go really, really far away from the origin, those lattice points move really, really far, right? Arc length. And that's not good for this code. Okay, correctable shift. So I mentioned there's a lot of lattices. This yellow region is the set of detectable shifts. However, not all of those are correctable. And correctable shifts are in one-to-one correspondence with eigenvalues of S1 and S2, which are the error syndromes. And these correspond to measuring partial information about the position and momentum of the oscillator. Position or momentum respectively, modulo let me get the factors of 2 right, modulo square root of pi. So you have some real number, you can always write it as square root of pi times some integer plus some remainder, right? And this is the error syndrome. And this is precisely the thing that the stabilizers wind up measuring. You don't want to measure any more than that because then you'll screw up the code superposition. If you measure the position exactly, you're going to collapse all the black or white balls into one ball. So this beautiful notion of error correction extracting just the right amount of information so as to diagnose where you are along this yellow line, but not anymore so that you collapse the code space and extract your logical information, is precisely measuring this modulo information about the position, and in terms of the argument that I did not make but said exists in terms of the momentum as well. However, the eigenvalues of the stabilizers are again modulo 2 pi, but this means that since we care about plus and minus shifts, this means that there's only this many different eigenvalues of S1 correspondingly S2 that we have access to. And so because we only have this many labels that we can extract, this many error syndromes, our set of correctable shifts is half as much as the set of detectable shifts. Very much similar to a code that detects errors on 2 qubits can correct an error on any 1 qubit. And now, sort of the elegant conclusion to this set of codes is that this is very much generalizable. We've looked at a set of stabilizers that lived all in one mode. And they corresponded to a lattice in position space that was formed by the code words. If you upgrade this position space to the phase space of the oscillator, namely you plot the position space as the x-axis and the momentum space as the p-axis, as the y-axis, then you get a 2D plane where S1 and S2, these stabilizers, correspond to generators of translations in this 2-dimensional lattice corresponding to the code. And now you can expand this idea to multiple modes by considering 2 n-dimensional lattices yielding an n-mode GKP code. It encodes a finite dimensional subspace into n modes, and it's generated by stabilizers that correspond to translations of symmetries of some lattice. You can use any lattice you want. If you're thinking Leach lattice, people have done that. There's some very, very crazy lattices out there, and they yield correspondingly nice exotic GKP codes on multiple modes. Yeah.
How do you physically measure the remainder R without moving X?
Good question. You have to generalize this C0 gate that we used to extract syndrome information for the repetition code. It's the same type of procedure. Now your degrees of freedom, however, are continuous variable. So you have to basically, what you do is you take an ancilla You have your, logical mode, whatever, and then you have some ancilla here. And this gate here, you can call it a conditional rotation, generalizing the C0 gate. And it wraps, and one easy way to do this is to make this be a circle. So they make this be planar rotor. There was a question about that. So make this state live in a particle on a ring, and this state is a particle on a line, and this C rod takes and winds around the line around the ring. And winding the line around the ring with specific periodicity removes this part of the story. Doesn't tell you about how many times, and only tells you this because that is the degree of freedom that's left that characterizes where you are on the ring. That's the elegant way to do it, but nobody has particle in a ring lying around in their lab. And so what they do wind up doing is they use an ancilla qubit here and extract the first bit of information about this R. Now you would think that that's not enough, that that's too coarse-grained. At least if you were me, you would have thought that. It turns out that is actually sufficient to yield a gain in the error correction over the bare unencoded mode. And this very nice experiment was done, I think, last year, and it's being implemented more this year at the Yale lab. And they're using an ancilla that has the bare minimum number of measurement outcomes for a code that was originally thought of as a very much continuous beast. So I thought that was really neat. So the experimentalists might often flip the table on you and basically tell you that your continuous variable stuff, you don't need it. You can just use a qubit anyway. Okay, now we'll do one more class of code, GKP stabilizer. Sure.
What do these displacement errors correspond to in terms of production?
Yeah, so if you exchange the black and white balls, you get a logical X in this position basis, and a logical bit flip. Because remember, their logical space is two-dimensional, so there's a logical bit flip that exchanges them. And then that exchange operation is done by, let's call it X logical, it's the square root of S2. And it's a shift by square root of pi. You can see that's exactly the amount you need to exchange the two balls. And a logical Z is the square root of S. That induces a minus sign next to the black balls. That's a logical Z error. These displacements give you Pauli type gates on GKP codes. More general, if you know what these are, Gaussian operations yield Clifford gates on the GKP codes. At least those, a subset of Gaussian operations that preserve the lattice, the overall lattice of black and white balls, yield Clifford operations on the GKP code. Yeah.
So this is just for one node.
Yes.
And so do you only get the like advantage if you go to multiple nodes? Is there some advantage to including one node?
Right, good. So one of the nice advantages in long term is combining these mode encodings with qubit encodings, namely concatenating, taking a qubit stabilizer code, NKD, and taking each physical qubit of that stabilizer code and putting that in a GKP encoding or another bosonic encoding of a particular mode. This yields an NKD code encoding K logical qubits in N modes. And this allows you to get two layers of error correction. You get all this continuous business on the lower level, and then you can use those continuous syndrome outcomes, all of these R's that I mentioned, on the higher level to better decode your NKD stabilizer code error. And that's one of the, I think, key advantages long-term. Now, a short-term advantage that the technology for bosonic codes allows you to do fairly, right now, is using GKP error correction to generate a logical error rate that goes below the physical error rate of the unencoded qubit. And this gives you a gain, which is sort of the ultimate goal of error correction, you think, is to increase the performance, increase the lifetime of your memory beyond what was physically available. And this is something that, again, people are actively working on now. As in a single mode, however, you are limited to how much you can increase the gain. There is a ceiling of how well this works. But if you go to NKD stabilizer codes, then there's something called a threshold theorem that tells you that you can scale up your resources, your N, to yield a gain that is arbitrarily large. Namely, there's no ceiling if you scale up modes or qubits in a tensor product fashion, but there is a ceiling if you do a single mode. So in that sense, GKP, few mode GKP, few mode bosonic codes are limited by the ceiling, but I believe that they should be a very integral part of future schemes that concatenate both bosonic and qubit codes. Did I tell you I would miss a factor of 2? This always happens. Where? Oh, this one? No, because that'd be a logical measurement outcome. Because you don't want to resolve the black and white balls, so you want to have a smaller set here. No, the set you're measuring here is this one. So that's the domain of R. Right? Yeah. All right. We got 12 minutes. Let's do the third class of codes, which is very similar to GKP code. But now we pivot again. So the first class of codes we looked at protected infinite dimensional logical space against arbitrarily large shifts in only a few modes. The second class of codes, the GKP codes, protected a finite dimensional logical space against sufficiently small displacements on all the modes. And this GKP stabilizer code is a hybrid version that allows you to protect, to some degree, an infinite dimensional subspace, an infinite dimensional logical space, against sufficiently small shifts on all the modes. This is something that was thought to be impossible until about 5 years ago, when a friend of mine and collaborators cooked this up. And it's very much based off of a GKP code. Now remember, a GKP code on on N modes consists of 2 N stabilizers. When we had one mode, we had to have 2 stabilizers that would, S1 and S2, one in the position, one in the momentum. When we have N modes, we need to have 2 N of them, and then we get a finite dimensional +1 joint eigenspace. If we take those 2 N stabilizers and start removing them, then we open up the space to be infinite dimensional. We no longer have enough, equations to give us a unique solution. We do have a partial lattice, but not one that gives us only a finite dimensional logical encoding. So you can think of as GKP stabilizer codes roughly as GKP codes with stabilizers removed. And this maintains some of the protection that we saw with GKP codes, namely protection against sufficiently small displacements, but it allows you to do so for an infinite dimensional logical space. So let's consider again a simple example. We're going to have a 2-mode GKP stabilizer group with S1 now corresponding to N equals 1. Capital N equals 1. So not in, so the, we're going to have stabilizer generators supported on mode 2 only. I'll just do the subscript labels here. Square root of 2 pi, N equals 1. So not 2 square root of pi, but square root of 2 pi. And this will be supported on mode 2 only. But we have 2 modes. Well, we don't do anything to the first mode at all. Our first mode is a logical mode. And we stabilize the second mode in a unique GKP comb state. It's a unique state because capital N is 1 in that mode, and there's only a one-dimensional +1 eigenspace stabilized on that mode. So our logical states as of now are just any old state on the first mode, tensor this GKP, fixed GKP state on the second. So this is the first step of the encoding. But we're not done yet because we have a lot of this error correcting stuff in the second mode. We have nothing. The first mode is just naked. So what we do is now we mix the modes a little bit. We torque the lattice a little bit, and we apply a beam splitter or a C-sum gate. And this C-sum gate can be defined as acting on the four quadratures associated with the two modes, namely x1, p1, x2, p2. And it transforms x1, it leaves x1 alone, transforms p1 to p1 minus p2, transforms x2 to x2 plus x1, and it leaves p2 alone. This way you mix or entangle the modes in such a way that the logical states I wrote here now become not separable states. And the way you do error correction in this code is at this point you apply the noise channel. So this is the part where you send it through the noise channel. I'm going to show you why these codes are beneficial. And the noise channel we're going to consider with these codes is the displacement noise channel. Which induces small shifts in all the quadratures. Small random shifts. And these random numbers are distributed with mean 0 and some standard deviation, sigma. And now once the noise is applied and the information has reached the other end of the noise channel, then we apply C-sum again. Decode. And finally, at the end, after this whole procedure, this winds up being the following. So the C-sum gate smears around the position of momentum P1 and X2. The displacements add little deltas to all the quadratures, and then the C-sum gate once more smears them around again. So at the end, in the Heisenberg picture, the full procedure is the following map. X1, nobody touches it except the noise. P1, well, P1 gets some noise of its own, but it gets some noise from the other one because of the C-sum gate. X2 gets some noise and gets some noise from X1. And P2 isn't really touched by the C-sum gate. Well, so the C-sum gate here is here in order to extract some of, or to move some of the noise from the other quadratures into X1, into X2. Remember, at the end here, we're left with some state on the first mode and a GKP state on the second. And we want to correct the state on the first mode as best as we can. The state on the first mode has undergone errors delta X1 and delta P1, and we want to extract those values and shift back as best as we can. Yeah.
C1 inverse, because C1 is not self-inverse.
Sorry, yes. Okay, so we want to correct delta x1 and we want to correct noise in these quadratures as best we can. And what do we have? Well, we have these quadratures and we have a GKP state on this second mode. And we can use this GKP state and measure its position and momentum modulo something in order to extract some information about these quadratures using this mode. That's the whole point of this. And there's, again, two sources of noise, so we need to recover against both. And to recover against, let's do the easy one first. To recover, let's first do the GKP measurements to extract the data. Yeah.
The noise will get cancelled out, like, except you cancel out in the private.
Well, because the shifts have added some linear shifts, so they don't get canceled out. They just get moved around.
Even when the P1 minus P2, that will go to P1 plus delta P1 minus P2 minus delta P2. Then when you see something else, then minus delta P2 plus delta P2.
So the noise adds a delta in each one. Yeah, it just goes x1 plus delta x1, p1 minus p2. Wait, sorry. Yes, so the new modes are these modes and the deltas are added to these modes.
So then it doesn't make sense to write delta P1 twice for the different modes again.
Where?
The x2 by 2, x2 plus delta x2 minus delta x1, x2 plus some delta x2. Some delta. This delta x1 has nothing to do with the delta x1.
I mean, this particular one does because the C-sum gate doesn't mix that. So I'm sticking with this convention because it does keep the P2 and the X1 there as the same. So the GKP measurements on mode 2 give us some partial information about the noise. There's two stabilizers we can measure for the GKP state, S1 and S2, and they give us two values. They give us X observed, which just gives us delta X2 delta minus delta X1. We're assuming these are very small so that the modulo measurement, the position, that this is literally the modular position, the position modulo square root of, pi. And so we just get this value. And similarly, P observed just gives us delta P2. So this is where I want you to see that the C-sum gate has been beneficial because it has leaked out some information about X1 into this quadrature that we can now measure. And then to recover, versus in momentum, of mode 1, which is the logical mode, remember, we apply a displacement on, so a position shift on mode 1 by delta P2. And this allows us to correct that part of the shift. It doesn't protect us against this one, but this one we would have obtained if we had a unencoded mode anyway. Remember, an unencoded mode just gets a delta P1 error. So what we've done is we've basically gone back to the unencoded case, and we've made it not any worse. Okay, so that's break even. Who cares, right? Well, let's look at what happens in the momentum case to recover partially in position, we use maximum likelihood estimates of the position shift. We don't have the position shift exactly because we have both delta x2 and delta x1, and we don't know either one. So we can't extract delta x1 to correct delta x1, but we can estimate it by assuming that the likeliest error was the one with the smallest delta. So we cook up an estimate for our delta x1 using our knowledge of x observed, which will be the solution to this problem, the minimum argument of the norm of the full position displacement vector, two norm. And now using our knowledge of delta x2, this is just x observed plus our unknown delta x1. And if we do this optimization, we get x observed over 2 times the minus as the estimate of what is the best or the maximum likelihood correction we need to apply, or maximum likelihood decoding we need to apply to mode 1. And then we apply a momentum shift on mode 1 by that amount that we calculate or that we estimated. And this converts our x, well, I'll do it up top with a different marker color. So now we apply this green thing, and that transforms our shift after you do the math. It's x1 plus half of delta x1 and delta x2. So in the end, summarizing, the noise that we've reduced our noise in our logical mode by P1 as follows. X1 has gone to x1 plus delta x1 plus delta x2. And P1 has not changed. So what's the point? Well, turns out, and this is the important point, delta x1 and delta x2 are random shifts. They're distributed around 0 with some standard deviation sigma. Let's say this is a normal distribution of mean 0, standard deviation sigma, delta xi. But delta x1 plus delta x2 over 2 is distributed around mean 0 with standard deviation sigma over 2. We reduced the fluctuations by half on average using the modular measurements of the GKP state and the C-sum gate to extract enough information about the noise so as to not reduce it completely, but to mitigate it in this random sense. And so this very cool observation can be generalized to other codes, to other types of GKP codes. It does allow you to mitigate quadrature noise in both quadratures. This one was the case of only the position one. More complicated codes allow you to do it in both, and there's active efforts by some of you in this room to develop codes that do similar things. So with that, I want to conclude and maybe take a couple questions.
Advantage here over the standard GDP code is that corrects over only the root pi, and the rest is not going to be anything.
The advantage here is that we're encoding an infinite dimensional logical space. You can formulate GKP-based error correction for finite dimensional logical spaces this way too, using this sort of distribution math. But here, the mitigation is done over an infinite dimensional space, which again, people did not think was possible.
I'm having a bit of trouble to understand how this setup is physical because you can't really choose when the noise will happen. Usually you would have thought you apply something, then you apply some logic gates or something like that, and then you will do something, then you will see some numbers afterwards. But then you're actually experiencing the computation that
Right. So, but you're going back to the roots of error correction. To demonstrate bare bones error correction, we have to assume perfect encoder and perfect decoder. And in between that is the noise channel, right? In lecture 1, we had this picture, right? The noise is here. And for pedagogical reasons, you at first assume this doesn't do any other noise. Of course, in the real world, you're totally right. You have to deal with the encoders messing you up, the decoders messing you up. But that's beyond the scope of these 3. I'm not going to be able to do that in 3 lectures. If you want to go even farther, the crypto people, they don't trust even the message sender, right? Somebody could have hijacked them and they're holding them at gunpoint and they're sending you the wrong message, So you can keep going, and the CS people love to do this. Yeah.
When you have like the software, can the same thing like air pressure
Yes, I've opened Pandora's box by alluding to that. So it's actually a really cool question. On one hand, you have cryptographic codes, which try to protect you against something you can think of as noise, but it's noise that's caused deliberately by some sort of human-based malicious observer. And on the other hand, you have error correcting codes where you're fighting against noise that's caused by some sort of underlying environment that is assumed to be out of the control of a human observer. Because if it was in the control, we wouldn't have to fight it, we could just eliminate it. And there is some work by, I think, for example, Joe Rennes at ETH, Zurich, where they try to develop connections and dualities between these different types of encodings. I think that's a really cool question, but I don't know much about this type of work. Anything in the chat?
Can you mention again what is GKP stabilizer equals GKP with access to mode?
Sure. Can I mention the connection between GKP stabilizer and GKP? Yeah, so with stabs removed, stabilizers removed. So a bona fide 2-mode GKP code would have 4 stabilizers on 2 modes. This one has only 2 stabilizers, but it's still defined on 2 modes. In that sense, I can think of it as a GKP code on 2 modes where I've removed both stabilizers for mode 1. Anything else?
Why not sigma over square root of sigma? And then
Oh, sorry. Yeah, that's sounds right. Correct. Half of the variance.
similar approach to mitigate delta P1,
Similar approach to.
mitigate momentum.
Yes, yes, yeah, there are. This is the simplest example that that people have thought of, and similar approaches allow you to do the same thing for both quadratures. To arbitrary, to even like not just a constant, but you need more overhead, you need more modes.
This is a similar analog to get from non-encode.
Well, there's an analog. I wouldn't call it very similar. Fermions are, in some sense, discrete objects. At least if you want to deal with, complex numbers and not Grassmann algebras. So there, the right analog is stabilizer codes. You just do something called the Jordan-Wigner transformation on stabilizer codes, and you get Majorana stabilizer codes. You can check those out in the error correction zoo. They're fairly well described there, or I guess the explanation is fairly long. I don't know if it's well written. You tell me. So there, you want to use Majorana operators, which are like Pauli matrices. They square one, and they anti-commute with each other. We did think of a Grassmann analog. Those of you who know Grassmann algebra, we tried to think of a Grassmann analog for GKP codes. We didn't succeed. If anybody's interested in doing that, I'd actually be happy to chat about that. That it? Okay. All right. Thanks, everybody. I'll put this up on online soon.